I'm gonna write it down just a little differently. So for problem number 35, they say f of x, okay? So they say f of x is equal to cosine of the cube root of 1 minus x. And so what, if I can make this some sort of composite function, okay? So I'm going to make it a really, I have to show that if I can make this a composite function of one or more functions, and then I can prove that each individual function is continuous, then the overall composite is continuous, okay? So what if I were to say something like, and I'm gonna go a little bit further so you guys can really truly get the hang of this. What if I were to say this is g of h of k of x. So I have g of h of k of x. So my first thing would be is what is the outermost function? There's really three functions listed in here.
Cosine of x.
Cosine of x?
Yes.
So I would say cosine of, and then I'm going to put these parentheses.
And then the cube root of x.
And then the cube root of x.
Okay, so then I would have the cube root of some stuff,
And then 1 minus x.
and then 1 minus x. Good. You guys seem to get the hang of this. Okay? So now what does that mean? Well, that means that g of x is equal to cosine of x, right? We said that h of x was equal to the cube root of x. And then we said that k of x was equal to 1 minus x. So in order for me to show that this is continuous, what do I have to prove? I have to show that g is continuous, h is continuous, and k is continuous. Because that makes, this is very informal language, g of h of k continuous. That was what Theorem 7 was about. Theorem 7 said, look, break this up into all of the components. It's a composite function, so break it up into its corresponding functions. Then go through, and if you could prove that this is continuous, that this is continuous, and that this is a continuous function, then the composite of all three is continuous. Is that right? So now, is cosine of x continuous?
Yes.
Yeah. What's the domain for that?
1, -1. Isn't it?
Yeah, so x is all reals, right?
Yeah.
Well, I can't do the thing there. But it goes from negative infinity to positive infinity, right?
Oh, yeah.
Can we take negative roots? In other words, can I take a cube root of a negative number?
Yes.
Yes, you can. When it's a cube root, you can. So this is also all reals. And we'll verify these things graphically too. 1 minus x. Any restrictions in the domain? No. All reals, all reals, all reals, continuous. Can I get a y value for everyone? In other words, if I plug in any value for x, will I get a corresponding y value? Yes. So this is continuous. This is continuous. And this is continuous. And so by Theorem 7 in your textbook, g of h of k is also continuous. Okay? So that's how you prove that it's continuous. So now let's unpack this. I'm really going to dive deep because you guys struggle with domain and range, and you also struggle with continuity. And by the way, when Mr. Adams learned this stuff, I struggle with those same concepts. So the first thing I want to do is I want to graph each one to kind of verify, okay? So if I say, and we know what these graphs look like. We've been looking at them for the last 4 or 5 years. God bless you. Cosine of x, graph it. Oh, got to zoom out a little bit here. Continuous. There's nothing wrong. There's no problems. There's no horizontal isotopes, right? So for every x value, there's a y value. There's no real problems with cosine of x, right? So that's continuous, always, for everything. So now I'm going to come back. Now I'm going to see if the cube root of x, now the one way I could write cube root of x is say x raised to what? 1 divided by 3. Again, all real numbers for the x domain. It's continuous throughout the whole thing. If I hit trace and I scroll through for every x value, there's a corresponding y value. It's a function. There's no problems with the continuity. No isotopes, no holes, none of that. No discontinuities. So again, I'm going to graph the third function, which is 1 minus x. This is just a linear function. It has a y-intercept of 1 with a slope of -1. Again, no issues. It's continuous throughout its entire domain. So now let's graph the whole thing. Now, if I graph the whole thing, I'm going to say cosine in parentheses. Now I'm going to set another set of parentheses, and I'm going to say 1 minus x. And to take the cube root of that, I'm going to raise that to the 1 divided by 3. Now I've got 1, 2, 3 open parentheses, so I need 1, 2.
That's it.
Is that it?
Yeah.
Are you sure?
Yep.
Yes.
Yeah, because I got another closed one right here. Alright, now we're going to hit graph. I'll zoom in a little bit because just to see if there's any, let's define it a little better. Okay, so now if I hit trace and I go through this whole thing, for every x value, there is a corresponding y value. So is this continuous? Yeah. And it makes sense, right? If you have a composite function that's continuous and you plug it inside another continuous function, it's going to be continuous. There's no restrictions. Just think about that from a common sense perspective. If any one of these functions that I plug into the main function cosine of x, if this had a domain restriction, that domain restriction gets carried with it to here, and that domain restriction gets carried with it. In other words, if this had a domain restriction, well, guess what? This will have a domain restriction. If this has a domain restriction, then guess what? This will have a domain restriction. So a discontinuity anywhere in the chain will cause a discontinuity for the whole function. Also, a continuous function inside of a continuous function is still continuous. And if you take one more and plug it into a third function that's continuous, then it'll be a continuous composite function. Okay? Does that make sense?